Imagine standing in the middle of a vast, silent plain at night, so dark and so wide that it seems to have no end. Then far away on the horizon, you notice a faint, ghostly glow. It's not bright enough to illuminate the ground, not sharp enough to show you where it comes from, but it's there, constant, ancient, and utterly unexplainable. That's what the cosmic microwave background is for astronomers. A faint afterglow stretched across the whole sky, a whisper from the very first moments of the universe. It's the oldest light we can ever see a photograph, not just of stars or galaxies, but of the universe itself, when it was still an infant, only a few 100,000 years old. And yet within this light there are strange imperfections, subtle distortions and blotches that suggest we might not be seeing the full picture. The cosmic microwave background, or CMB, isn't something you can look up and see with your own eyes. It's not a dramatic swath of glowing stars or swirling colors like you'd find in a Hubble photo. In fact, if you could see it directly, it would look completely uniform to you, a soft haze in every direction. But when scientists point their most sensitive radio telescopes toward it, the picture changes. What appears to be a smooth blanket of faint radiation is actually speckled with tiny temperature variations. Differences so small, they measure just millionths of a degree. Those variations form a kind of thermal map of the young universe, like ripples frozen in time. To us, it's more than just a map, it's proof. Proof that the Big Bang happened, that space and time themselves had a beginning. Without the CMB, the Big Bang would still be a debated hypothesis, a beautiful but unconfirmed story about cosmic origins. With it, the evidence becomes unavoidable. It's the fossil light of creation, the first light to escape after the universe cooled enough to let photons travel freely, no longer trapped in a dense soup of particles. That light has been traveling ever since, stretched into microwave wavelengths by billions of years of cosmic expansion. But here's where the story turns from awe-inspiring to unsettling. The CMB isn't perfect. For decades, cosmologists have been mapping it with increasing precision, and with every new layer of detail they uncover, the picture grows stranger. Amid the random scatter of hot and cold spots, certain patterns seem wrong. There are alignments that shouldn't exist if the universe is truly uniform on large scales. There are regions that appear colder or hotter than statistical chance should allow. And then there are the blotches, areas that defy the neat predictions of the simplest cosmological models. It's as if you found an ancient painting in a museum, one that scholars had agreed was a masterpiece from the dawn of human civilization. And in the middle of it, behind centuries of dust and faded pigment, there's a shadowy figure that no one can account for. A figure that might have been painted there intentionally, or might have appeared later by forces unknown. Would you be able to look away? Some of these CMB anomalies could have simple explanations. They might be statistical flukes, the sort of rare coincidences that become inevitable if you look at enough data. They might be caused by foreground interference, cosmic dust, or gas clouds in our own galaxy, subtly distorting the signal. But what if they aren't? What if those irregularities are the faint, distorted edges of something far more profound? One idea, and it's not the kind that lets you sleep easily at night, is that behind the CMB there could be structures from a time and place we can't otherwise access. Not galaxies or nebulae as we know them, but vast unseen regions that existed before or beyond the Big Bang itself. The light from the CMB could be hiding evidence of collisions with other bubble universes, scars from an ancient impact in the sea of space-time. Or it could be concealing the gravitational pull of something unimaginably massive, bending the fabric of the early universe before light even had a chance to scatter. The thought is dizzying because the CMB is supposed to be our limit, the farthest wall we can ever observe. Beyond it, the universe was opaque, its light trapped. We can never see further back in time with traditional observation. And yet these anomalies suggest that maybe, just maybe, we can feel the shadow of something on the other side of that wall, something pressing against it, leaving faint fingerprints in the oldest light. This is where the real tension lies. If the CMB does hide a deeper reality, then the foundations of modern cosmology may not just be incomplete, they may be fundamentally wrong. Every equation, every model, every beautiful computer simulation we've built to describe the universe rests on the assumption that what we see in the CMB is a clear, honest record of the early cosmos. If that record is flawed, if it has been edited or altered by events we don't yet understand, then the story of the universe might have a completely different first chapter than we thought. And yet there's a poetic kind of trap here. Because the CMB is both the oldest thing we can see and the ultimate cosmic horizon, we may never be able to directly look past it. It is a wall made of light, a boundary drawn by the very physics that makes our observations possible. If something lurks behind it, it hides, not because it's malicious, but because the universe itself refuses to let that light through. That's what makes it terrifying, the possibility that answers to the greatest mysteries are there just out of reach, separated from us by the laws of nature themselves. Still, the human mind is not one to accept a closed door. Scientists have learned to read the CMB in subtler ways, to search for tiny deviations in its texture, its polarization, its statistical distribution, hoping to glimpse a pattern that doesn't belong. Sometimes they find something odd. Sometimes they dismiss it as noise. But every so often the oddities refuse to vanish, and the whispers from the farthest edge of time become louder. So here we stand looking at a map of the universe, when it was still a glowing mist, long before stars were born, long before planets formed, long before any mind could contemplate its own origins. We stare at this map and see the marks of processes so vast, so ancient, that they make our entire history seem like a flicker. And in the middle of this glowing fog, in the subtle shifts of color and temperature, there might be the outline of something waiting to be discovered, something that could change everything we know about where we came from and where we are going. But before we can even begin to ask what's hiding behind that ancient curtain, we need to understand what the curtain is made of. We need to know how the CMB was born, how it came to fill the universe with its faint but eternal glow, and why it holds such power over our understanding of reality. Only then can we hope to see past it, or at least to know why we never will. Close your eyes and imagine a darkness so complete it is not just the absence of light, but the absence of space, time, and even the concept of before. Then, without warning, a single instant shatters the void. An eruption so powerful that it doesn't just light up the darkness, it creates the very stage upon which light itself can exist. This was the Big Bang. Not an explosion in the conventional sense, but the sudden expansion of all that would ever be. Every particle, every force, every dimension of reality bursting forth in less than the blink of an eye. And though the event took place 8 billion years ago, its aftershocks are still with us, woven into the very fabric of the cosmos, in the form of a faint, nearly invisible glow. That glow is the cosmic microwave background, and it is nothing less than the echo of creation itself. The CMB is not light in the way we usually think of it. Not the sharp golden blaze of a star, not the silvery shimmer of the moon, but something far older and colder. To understand it, imagine standing in a vast, pitch-black room, your ears ringing from a firework that exploded only moments ago. Even after the sound has faded, the air still vibrates faintly, carrying the memory of what happened. In much the same way, the CMB is the lingering vibration of the universe's birth, stretched and softened by eons of expansion, until it now hums gently in the microwave portion of the electromagnetic spectrum. In the very first moments after the Big Bang, the universe was a seething, opaque plasma, an ocean of high-energy particles where photons could not travel freely. Every bit of light collided almost instantly with electrons and protons scattering and bouncing so often that the cosmos was in effect blind to itself. It took roughly 3,800,000 years for things to calm enough for protons and electrons to combine into neutral hydrogen atoms. This moment is called recombination, and it was the first time light could move without being immediately stopped. The photons that escaped then have been traveling ever since, their energy steadily drained by the stretching of space itself. What began as searing, blinding radiation has cooled to a temperature just above absolute zero, invisible to human eyes, but unmistakable to the instruments we've built to find it. The discovery of the CMB was fittingly a kind of accident. In the mid-1962, two radio astronomers Arno Penzias and Robert Wilson were working with a sensitive microwave antenna in New Jersey. No matter where they pointed it, they detected a persistent background hiss. They cleaned the antenna, adjusted the electronics, even chased away pigeons that had made a home in the equipment, but the signal remained. What they had stumbled upon was not local noise, not the byproduct of the Earth or the Sun, but the glow of the universe's earliest light. Without knowing it, they had tuned into the whisper of the Big Bang. This whisper carries far more than just poetic significance. Encoded in the CMB's faint variations is a detailed record of how matter and energy were distributed in the young universe. Each tiny hotspot represents a region where matter was ever so slightly denser, destined to one day collapse into stars, galaxies, and eventually us. Each cold spot marks a region where matter was thinner, where the pull of gravity would be weaker, shaping the great voids between the cosmic structures we see today. The CMB is like a baby picture of the cosmos, and from that picture, cosmologists can reconstruct an astonishing amount of its biography. By analyzing the CMB, scientists can measure the precise proportions of ordinary matter, and dark energy that make up the universe. They can determine its age with remarkable accuracy and understand the rate at which it has been expanding since the beginning. The ripples in the CMB are also the fingerprints of sound waves, literal acoustic oscillations that rippled through the hot plasma of the early universe. These baryon acoustic oscillations leave behind a telltale spacing in the distribution of galaxies, an imprint that continues to guide our understanding of cosmic structure formation. But perhaps the most mind-bending aspect is that the CMB also lets us glimpse physics at energies far beyond what any human-made experiment could reach. The patterns in its fluctuations tell us about conditions just fractions of a second after the Big Bang, a time when the universe underwent a burst of hyperinflation, a rapid expansion that smoothed space while seeding the minute, irregularities that would grow into everything we see today. Those irregularities, magnified over billions of years, are the reason the universe is not perfectly featureless. Without them, there would be no stars, no planets, and certainly no life. In this sense, the CMB is both a beginning and an ending. It marks the end of the universe's opaque, blindingly hot youth, and the beginning of a transparent cosmos where light could roam free. But it also represents the farthest wall we can ever see, because before recombination, the universe was impenetrable to photons. It's the ultimate horizon of sight, the last curtain before the lights came on. Beyond it, the cosmos is locked away, accessible only through indirect clues. When you look at a high-resolution map of the CMB, a strange mottled pattern of reds and blues representing tiny temperature differences, you're looking at a portrait of the universe's first visible moment. The reds mark slightly warmer, denser patches, the blues slightly cooler, sparser ones. Together they tell a story of balance and imbalance, of forces tugging and yielding, of gravity and pressure engaged in a cosmic dance. And from this map, scientists have been able to write the opening chapters of the universe's story with astonishing detail. Yet there is an odd fragility to this achievement. We trust the CMB to be an honest record of the early universe, but that trust is exactly what makes the anomalies so disturbing. If the CMB is a perfect echo of the Big Bang, then everything we've built in modern cosmology stands on solid ground. But if there is something in the way, something distorting, editing, or adding to that ancient signal, then what we think of as the cosmic truth might be incomplete or worse, misleading. For now, the CMB remains one of the most successful and deeply studied pieces of evidence in all of science. It is a beacon from a time when the universe was young and raw, a time before stars had lit their first fires, before galaxies had begun their slow spirals. It's the ultimate message in a bottle sent across billions of years, carrying the soundless echo of the universe's birth. But as with any message, the question is whether we've read it correctly. As instruments grow sharper and our maps of the CMB gain finer detail, the anomalies become harder to ignore. Strange cold spots, unexpected alignments, subtle asymmetries, each one is a tiny crack in the smooth surface of the early universe. And once you start seeing cracks, you can't help but wonder what might be on the other side. That is the mystery waiting beyond the CMB's beauty, and it's what leads us directly to the next, more unsettling question. Because when scientists stared deeper into that ancient map, they found something that didn't belong, something that didn't fit neatly into the story of the Big Bang at all. There is a place in the universe where the warmth of creation seems to falter a patch in the cosmic microwave background, so vast and so cold that it feels like a scar on the face of the cosmos itself. When scientists first mapped the CMB with enough precision to notice its fine details, they expected to find a mottled pattern of hot and cold spots, each corresponding to tiny fluctuations in the density of matter shortly after the Big Blast and the Deng. Bang! What they did not expect was the cold spot, a region so much larger and colder than statistical chance should allow, that it immediately demanded explanation. This is not the kind of cold you and I know. In human terms, the entire CMB is already unimaginably frigid, sitting at just 2.725 degrees above absolute zero. But within that faint glow, differences as small as 100,000th of a degree matter. They are the fingerprints of the early universe's structure, the seeds from which galaxies grew. The cold spot is not merely one of those tiny variations. It is an expanse billions of light years across, cooler than its surroundings by a measurable, persistent amount. If the CMB is the baby picture of the cosmos, this is like finding an oddly dark bruise covering a huge portion of the frame. When astronomers first confirmed the cold spot's existence, the simplest explanation was that it might be nothing more than a statistical anomaly, a cosmic coincidence produced by random fluctuations in the early plasma. After all, if you roll the cosmic dice enough times, rare outcomes will appear. But as measurements improved, the odds of it being pure chance shrank dramatically. It began to look less like a quirk of randomness and more like a deliberate imprint, the sign of something physical that shaped the universe in its infancy. One of the first serious attempts to explain it focused on the idea of a supervoid, an enormous underdense region of space in the present-day universe. If the cold spot lies in the direction of such a void, then light traveling through that vast emptiness would lose a tiny bit of energy, cooling ever so slightly by the time it reached us. This effect, known as the integrated Sachs-Wolfe effect, could account for part of the cold spot's temperature drop. Surveys of galaxies in the region did in fact reveal a supervoid stretching hundreds of millions of light-years across. For a time it seemed this might be the answer, but the numbers didn't add up. The supervoid was real, but it wasn't nearly big or deep enough to explain the magnitude of the cold spot. The temperature difference remained too great, too stubborn, to fit neatly into the known physics of large-scale cosmic structures. That's when other, more unsettling possibilities began to emerge. Among these is the idea that the cold spot might be the lingering mark of a collision between our universe and another. If the theory of eternal inflation is correct, then the Big Bang was not a unique event. Instead, space itself has been bubbling with pocket universes, each with its own laws of physics, springing into existence within an ever-expanding multiverse. Occasionally, two such bubbles might collide. If that happened to ours in its earliest moments, the impact could have left an enormous asymmetric imprint in the CMB, precisely the kind of anomaly the cold spot represents. This is where the cold spot begins to feel less like a data point and more like a door. Because if it truly is evidence of a collision with another universe, then we are not alone in the deepest possible sense. There could be other realms of space and time beyond our cosmic horizon, each with its own galaxies, stars, perhaps even life, all forever out of reach, but capable of leaving scars on our sky. Of course, extraordinary claims demand extraordinary evidence, and so far the cold spot remains a tantalizing but inconclusive clue. Some researchers remain convinced that it is a statistical fluke, after all a reminder that humans are wired to see patterns even when none exist. Others argue that it may be a sign of physics we have yet to discover, perhaps tied to exotic forms of matter or energy that behave strangely in the early universe. But let's step back for a moment. Imagine for your own sake the scale of what we are talking about. The cold spot spans about 1.8 billion light-years in diameter. Light, the fastest thing we know, would take nearly 2 billion years just to cross from one edge to the other. If a spaceship left Earth today traveling at the speed of light, it would still be making that journey when our sun had long since died. This isn't just a hole in the map. It's an absence so vast that it defies the human sense of proportion. And yet we can see it not with our eyes but with the instruments that capture the oldest light in existence. That in itself is astonishing. It means we are capable of detecting imperfections imprinted when the universe was less than 500,000 years old, and tracing their consequences across nearly 14 billion years of cosmic history. Some nights, when the thought lingers too long, the cold spot can feel almost personal. If there was indeed another universe brushing against ours, then in a strange way we've been touched by something alien, something utterly outside the reality we know. And that touch is still visible, preserved in the sky like a fossil in stone. Yet it's also possible, and this is equally unsettling, that the cold spot's true nature will never be known. It may remain forever in the liminal space between chance and necessity, between the ordinary and the extraordinary. Perhaps the most terrifying thing is not that it points to another universe, but that it points to a limit in our ability to ever be sure. This is the tension at the heart of cosmology. The universe offers clues but never the whole truth. Every new observation sharpens the picture, but also reveals new shadows. And in the case of the cold spot, those shadows lead directly toward the biggest questions of all questions about whether our universe is unique, whether reality is larger than the space we can see, whether the cosmic story we tell ourselves is only one chapter in an endless library. If the cold spot is a scar from another universe's collision with ours, then it is the first tangible evidence that the multiverse might be real. And if it is, then our place in reality is far stranger and far smaller than we've dared to imagine. The map of the universe would be just one map among many its borders, not edges but intersections. Our sky would not be a ceiling but a boundary we share with something else, something unimaginably vast. And yet, if it is nothing more than a quirk of random fluctuations, that too tells a story about how even in the most uniform and well-understood phenomena, the universe still has room for surprises. It means we can never take the smoothness of the cosmos for granted. There will always be places where the rules seem to bend, where the order we expect is broken by an unexpected gap, a blotch, a scar. Either way, the cold spot forces us to look again at the sky, to wonder what else might be hiding there, waiting to be found. Because if one anomaly this large can exist, there may be others, and the next one might not be so easily explained. From here, the trail leads into deeper waters, into theories that stretch our imagination to the breaking point, into possibilities that blend science with the wildest speculation. If the cold spot is a whisper from another universe, then what does that say about the nature of reality itself? And if such realms exist, how might they touch ours in ways we have yet to notice? Those are the questions waiting just ahead. Because if this scar on the CMB is truly what some believe, then it is not only a mark of our past, it may be the first signpost pointing us toward a much greater, stranger multiverse. Imagine for a moment that our universe is not the whole of reality, but merely a bubble floating in an endless cosmic ocean. This is not just poetic imagery. In some of the most compelling models of cosmic inflation space, itself undergoes a rapid, exponential expansion, spawning countless pocket universes in the process. Each one forms as a bubble within this vast expanse, sealed off from the others by horizons of space-time we cannot cross. Our own observable universe, then, is the interior of just one such bubble, and the cosmic microwave background is like the thin, glowing membrane marking its edge, the farthest surface we can possibly see. From this perspective, the CMB is not merely a relic of the Big Bang, but a kind of cosmic boundary. It is the skin of our bubble frozen in time, from when light first became free to travel through space. Everything beyond it is unobservable, forever hidden behind the limits of light's reach. And yet, despite being sealed off, our bubble may not be entirely untouched. The inflationary models predict that other universes can, and sometimes do, collide with ours. When two bubbles crash together, the energy of the collision ripples through their structures, distorting the delicate patterns imprinted on their cosmic backgrounds. Theoretically, such an impact could leave a faint but unmistakable signature, a kind of birthmark in the CMB we observe today. This is where the cold spot begins to make a kind of narrative sense. If it is indeed a remnant of such a collision, then it is evidence of a moment when our universe was not alone in its infancy. Picture it somewhere in that eternal ocean. Another bubble had formed, expanding just as ours did, perhaps with its own galaxies and stars, perhaps with nothing but empty space. As it swelled, it drifted closer to ours, until inevitably their edges met. The interaction would have been catastrophic on a cosmic scale, yet subtle in the sense that most of what followed the formation of galaxies, the dance of planets, could still proceed largely undisturbed inside each bubble. The only lasting mark might be a warped cooler patch in the glow of the CMB, preserved like a scar for billions of years. The very possibility shakes the foundations of science. Physics at its heart seeks universal laws, rules that apply everywhere and always. But if the multiverse exists, those rules may be local rather than universal. Each bubble could have its own constants, its own forces, its own chemistry, even its own versions of time and space. Some might be sterile, lifeless expanses. Others could be so alien that we wouldn't recognize their physics at all. And a few perhaps might resemble ours closely enough that life, intelligence, and civilizations could arise. Which brings us to the question that's harder to dismiss than it is to answer: if there are other universes, if our cosmos has siblings, could they know we exist? We know our bubble has limits. We cannot send signals across its walls. Even light cannot escape the bounds of our horizon. But what if during a collision some kind of exchange occurred? Could matter or energy have passed between universes, altering the course of their histories in ways neither could control? Could a trace of us exist somewhere beyond our sky, just as a trace of them might exist in the cold spot? The thought is intoxicating and troubling in equal measure. On one hand, it reframes our place in reality not as the center of all things, but as one of countless isolated islands. On the other, it raises the haunting possibility that contact, true mutual awareness between universes, might be impossible. We might be like ships passing in a boundless night, leaving only a faint swell in each other's wake. Of course, to many scientists, this is still speculation balanced precariously on theory. The physics of inflation is elegant and supported by much observational evidence, but the step from inflation to multiple universes is enormous. Some argue that until we have direct, testable predictions about bubble collisions, the multiverse will remain more philosophy than science. Others point to anomalies like the cold spot and say here perhaps is the first tangible clue. Even if we can't yet prove the cause, its very existence invites explanations that stretch beyond the comfortable boundaries of a single universe worldview. Still, we are left with the sobering fact that if these other universes exist, most will be forever hidden. The cosmic horizon is not a wall we can break, no matter how far technology advances. The laws of relativity simply do not allow it. The CMB is the last light we will ever see from the early universe, and beyond it we can only infer, imagine, and model. It is quite literally the curtain of the multiverse, and for now it is drawn. Yet the human mind is restless in the face of such limits. We build telescopes that stretch our vision satellites, that map the faintest afterglow, computers that simulate what cannot be touched. We look at a tiny temperature anomaly billions of light years away and dare to wonder if it is the handprint of another reality. We are creatures who have barely stepped beyond our own moon, yet we speculate about infinite oceans of space-time, each dotted with universes like beads of dew. That is the kind of audacity the multiverse invites. But there is also humility in this idea. If reality is so much larger than what we see, then our stories, all the human dramas, triumphs and tragedies unfold on a stage far smaller than we ever imagined. We may be important to ourselves, but in the grand ledger of existence, we are one note in a symphony we cannot fully hear. And perhaps that is why we keep searching, not because we expect an answer soon, but because each glimpse beyond our current horizon, even a theoretical one, deepens the mystery and reminds us that there is more to learn. For now, the CMB remains our best tool for peeking behind the curtain. Its patterns frozen since the dawn of time carry within them the record of everything that happened in those first critical moments. If a bubble collision occurred, the CMB would bear its fingerprint. And so we keep scanning, refining our measurements, and pushing the limits of what we can extract from that ancient light. Maybe the cold spot is the first hint. Maybe there are others we have not yet recognized. And so the question hangs in the air. Are we alone in our bubble? Or have we brushed against other worlds in the dark? The answer, if it comes, may change not only our understanding of the universe, but our understanding of reality itself. Yet even as we dream about worlds beyond our cosmic shores, we must not forget that some of the greatest mysteries are right here within the bounds of our own bubble. In fact, there is something in our universe, something all around us, that is invisible, untouchable, and yet outweighs everything we can see. It does not glow in the CMB or shine from the stars, but it shapes the fate of galaxies and perhaps the fate of the cosmos itself. And to uncover that story, we must turn our gaze inward, away from the edges of the multiverse, and into the hidden heart of our own universe. If you were to take all the stars, planets, gas clouds, and glowing galaxies in the cosmos and pile them together into one unimaginably vast scale, you might expect that to be the bulk of the universe's mass. After all, it's everything. We can see everything that shines or reflects light. But when scientists used the cosmic microwave background as a kind of cosmic weigh-in, the result was startling. The visible matter, the stuff that makes up you, me, and everything we've ever observed, is only a tiny fraction of the total. Most of the weight of the universe comes from something utterly invisible, something that neither emits nor reflects light. This mysterious majority is what we call dark matter. The name makes it sound sinister, but it's really just shorthand, for we have no idea what this stuff is. Dark matter does not behave like ordinary matter. It does not glow, cannot be photographed, and passes through solid objects without leaving a trace. Yet its gravitational pull is undeniable. Galaxies spin in ways that defy the laws of physics if we only account for visible matter as if they are held together by an unseen scaffolding. Galaxy clusters bend light more strongly than they should, creating cosmic lenses that can magnify distant galaxies far beyond what visible mass can explain. Even in the earliest moments after the Big Bang, the influence of dark matter shaped the growth of cosmic structure. The CMB plays a crucial role in revealing this hidden presence. Those faint patterns, the tiny variations in temperature and density frozen into the background glow, encode the physics of the young universe. By studying them, scientists can calculate how much matter was present at the time, how it was distributed, and how it influenced the formation of galaxies. The numbers are unambiguous. About 85% of the matter in the cosmos is dark matter. Only 15% is the ordinary matter that makes up atoms, molecules, and everything familiar to us. This means that, in a very real sense, most of the universe is made of something we have never seen, something that interacts primarily through gravity. And here's where the mystery deepens. If dark matter interacts with ordinary matter only through gravity, it should be almost impossible to detect directly. But what if it has other subtler interactions? The CMB offers one of the best chances to find out. If dark matter can interact with light, not the visible kind we see today, but the ancient photons of the CMB, it might leave faint fingerprints in that primordial glow. Slight distortions, unexpected shadows, or tiny shifts in the energy of the CMB could all hint at the nature of dark matter. Some scientists suspect that certain theoretical particles like axions or sterile neutrinos could make up dark matter. These particles would be almost ghost-like, passing through normal matter, without collision yet subtly affecting light, in ways we could measure with exquisitely sensitive instruments. Others imagine dark matter might have its own forces and interactions. An entire dark sector with physics as rich and complex as the visible universe. If that's true, then dark matter might not be entirely passive. It could clump form structures, even create dark stars powered by interactions we cannot yet observe. The CMB might be our first faint glimpse into this hidden world. But here's where the story gets more unsettling. If 85% of the matter in the universe is invisible, then everything we have built our understanding upon, from the life cycle of stars to the large-scale evolution of the cosmos, rests on a framework we do not yet understand. We are like sailors navigating by the shapes of waves, guessing at the vast currents beneath the surface. Dark matter is the deep ocean of the cosmos, and all our galaxies are just ships riding its invisible swells. The hunt for dark matter is relentless. Detectors buried deep underground listen for the faintest whispers of interaction between dark matter particles and atoms. Space-based observatories scan the skies for gamma rays or X-rays that could be produced when dark matter particles collide and annihilate each other. And the CMB, the oldest light in the universe, is scrutinized with ever-increasing precision in the hope that somewhere in its ancient patterns lies the clue that will break the mystery wide open. For now, the evidence remains indirect but overwhelming. We cannot see dark matter, but we can see what it does. It holds galaxies together against the pull of their own rotation. It sculpts the cosmic web, the vast filaments of galaxies stretching across billions of light years. It shaped the seeds of cosmic structure in the infant universe, guiding matter into the clusters and superclusters we see today. Without it, the universe as we know it could not exist. Still, one question keeps tugging at the mind. What if dark matter is not a single thing? What if the term dark matter hides a whole zoo of unknown entities, just as ordinary matter includes protons, neutrons, electrons, and countless composite particles? In that case, the CMB might be telling us more than we realize. Different types of dark matter would have left different imprints in the young universe. The challenge is to read those imprints without assuming too much about what we expect to find. This is where imagination must work hand in hand with precision. We must consider the possibility that dark matter is stranger than any particle we've yet theorized, perhaps something that changes its behavior over cosmic time. Maybe it interacted strongly with light in the early universe, leaving behind detectable traces in the CMB, but has since become almost perfectly invisible. Or perhaps it exists in forms that could never interact with light at all, leaving only its gravitational signature for us to puzzle over. The search for answers is more than just an exercise in physics. It's a reminder of how incomplete our view of the universe really is. The stars and galaxies we admire are just the glittering foam on the surface of a much deeper reality. Somewhere out there and all around us is the mass that shapes the cosmos, unseen and largely unknown. And yet, even as we push toward understanding dark matter, we know it is only part of the unseen universe. There is something even more elusive, something that doesn't just add to the mass of the cosmos, but drives its very expansion. If dark matter is the ghostly scaffolding holding the universe together, then this other force is its opposite, a kind of cosmic anti-gravity pulling everything apart faster and faster. It does not bind but unbinds, stretching the fabric of space itself. We call it dark energy, and its effects are written not in the CMB's patterns of matter, but in the accelerating growth of the universe itself. To understand it, we will have to look not only at the relic light of the Big Bang, but at the motion of galaxies across billions of years. And that story may be even stranger than the one we've just told. If dark matter is the hidden scaffolding that holds the universe together, then dark energy is the mysterious force that seems determined to tear it apart. Unlike anything else we have encountered in physics, dark energy is not a form of matter, not a cloud of invisible particles drifting between galaxies. It is something woven into the very fabric of space itself, a pressure that pushes outward, stretching the cosmos faster and faster as time goes on. It does not pull like gravity, it repels, and in doing so, it has reshaped our understanding of the universe's destiny. The cosmic microwave background, that ancient afterglow from 13.8 billion years ago, serves as our earliest record of cosmic expansion. By studying its subtle fluctuations, scientists can measure the speed at which the universe was growing in its infancy. These measurements are stunningly precise. The CMB is like a snapshot of the cosmos when it was just 380000 years old, frozen in time. From that starting point, we can use our best models of physics to predict how quickly the universe should be expanding today. But here's the twist: when we compare those predictions to what astronomers actually observe in the modern universe, the numbers don't match. This discrepancy is not small, it's large enough to make physicists lose sleep at night. Using supernova explosions as cosmic mile markers, galaxy surveys to track the large-scale structure of space, and precise measurements of how galaxies move away from each other, we consistently find that the universe is expanding faster than the CMB-based models predict. This mismatch has become one of the most perplexing puzzles in cosmology, known as the Hubble tension. If the laws of physics have been constant since the dawn of time, the early universe's expansion rate and the modern universe's acceleration should align perfectly. The fact that they don't suggests one of two unsettling possibilities: either our understanding of cosmic physics is incomplete, or the very nature of space and time has changed over the eons. In other words, something profound happened between then and now, something our equations don't yet capture. Dark energy is our placeholder name for that something. We first discovered its effects in the late 1992, when two independent teams studying distant supernovae found that the universe's expansion wasn't slowing down under gravity's pull, as expected, but speeding up. This was a complete shock. The simplest explanation was that there exists some form of energy inherent to space itself, an energy that doesn't dilute as the universe grows, but instead exerts a constant repulsive pressure. If space expands, more space appears, and with it more dark energy, leading to a runaway effect where expansion accelerates forever. But this explanation opens up deeper mysteries. Why should empty space have energy at all? In quantum physics, the vacuum is not truly empty. It's a seething foam of virtual particles popping in and out of existence. But the energy predicted from this vacuum fluctuation is so enormous it would blow the universe apart instantly. The dark energy we observe is tiny by comparison, smaller by an almost incomprehensible factor. This mismatch between theory and observation is one of the biggest unsolved problems in science, sometimes called the worst prediction in physics. The CMB gives us another way to probe dark energy's nature. By tracing the growth of cosmic structure over billions of years, it allows scientists to see how the tug-of-war between gravity and dark energy has played out. In the early universe, matter was dense enough to dominate and expansion slowed. Over time, as the universe thinned out, dark energy took over and expansion began to accelerate. The exact moment of this cosmic handover is written in the way the CMB's patterns match or fail to match the distribution of galaxies we see today. Any deviation could point to something even stranger. Perhaps dark energy changes with time, growing stronger or weaker as the universe evolves. Some theories propose that dark energy is not a fixed property of space, but a dynamic field, one that shifts and flows, perhaps even interacting with dark matter in ways we have not yet detected. Others suggest that we don't need dark energy at all. Instead, what we call acceleration might be a sign that Einstein's theory of gravity breaks down at the largest scales, and the geometry of space-time itself behaves differently than we thought. These ideas are radical, but the Hubble tension is pushing more and more scientists to consider them seriously. And then there's the most unsettling possibility that the constants of nature, the unchanging numbers we thought governed the cosmos from the beginning, may not be constant at all. If the strength of gravity, the speed of light, or other fundamental values have drifted over billions of years, the mismatch between early and late expansion rates could be a symptom of that cosmic drift. Such a discovery would force us to rewrite physics from the ground up, not just for cosmology, but for every branch of science. For now, dark energy remains a name, not an explanation. We can measure its effects with exquisite precision, we know. It makes up about 68% of the total energy content of the universe. But we cannot say what it actually is. It might be eternal, dooming the cosmos to expand faster and faster until galaxies vanish from each other's view and the night sky grows empty. Or it might be temporary, fading over time, and allowing gravity to pull the universe back together in a distant big crunch. The stakes are enormous, because understanding dark energy means understanding the ultimate fate of everything. If it remains constant, the cosmos will become increasingly lonely, each galaxy retreating beyond the reach of light until they disappear forever. If it changes, the universe's story could take turns we cannot yet imagine. The CMB is our oldest witness, but even it can only tell part of the tale. To uncover the rest, we must look not only backward to the Big Bang, but forward, and perhaps sideways to see if the clues lie in the very origins of time itself. And that raises an even stranger thought. What if the secret of dark energy is not in the history of the universe after the Big Bang, but in whatever existed before it? Could the acceleration we see today be the echo of a pre-Big Bang, state a leftover pressure from a cosmic phase we have not yet imagined? If so, the CMB might be whispering to us not just about the birth of our universe, but about a time before that birth, a time we have yet to truly comprehend. That question, more than any other, pulls us into the next mystery, one that reaches beyond the beginning of everything we know. For most of human history, asking what happened before the Big Bang was like asking what's north of the North Pole. It seemed to be a question with no meaning, a place where the map simply stopped. The Big Bang, we were told, was not just the beginning of matter and energy, but of time itself. There was no before because time had no prior moments in which events could occur. For decades, cosmology treated this as settled truth. But science has a way of prying open even the most firmly locked doors. And in recent years, new ideas have started to suggest that the story might not be so simple. Some cosmological models propose that our universe is not a one-time event, but part of an eternal cycle, expanding, slowing, contracting, and then exploding outward again in a new Big Bang. In such a cyclic universe, what we think of as the birth of everything might just be the latest chapter in an infinite series of cosmic epochs. The death of one universe would give rise to the next, over and over, perhaps forever. If that is the case, then the cosmic microwave background might be more than the afterglow of our own universe's birth. It could carry faint imprints from a universe that existed before ours, tiny echoes from a time before time. The CMB's pattern of temperature fluctuations, those subtle mottled patches across the sky, might contain traces of structures or events that survived the cosmic reset. The idea is almost unbelievable, but it is not without precedent in physics. Energy and information in certain conditions can survive transitions between states, leaving signatures that persist long after the original source is gone. One of the most tantalizing proposals comes from a concept called conformal cyclic cosmology, championed by mathematician Roger Penrose. In this view, each universe in the cycle eventually stretches itself so thin and so empty that time, in a sense, loses its meaning. In that final state, the dying universe becomes indistinguishable from the hot, dense conditions at the start of the next one. The transition is seamless. The end is the beginning, and some information from one aeon could pass into the next, like a whispered message across the boundary of time. Penrose has even claimed to see hints of these messages in the CMB in the form of unusual circular patterns that could be the ghostly remains of supermassive black holes from a previous universe. If such evidence exists, it would shake the very foundations of cosmology. The idea that the Big Bang was not the beginning, but simply a bridge between universes, would rewrite our understanding of reality. The concept of a beginning would become an illusion, a convenient marker in an endless cosmic chain. In that light, the CMB transforms from a baby picture of our universe into something stranger, an archive, a cosmic palimpsest where the ink of previous histories faintly bleeds through. But there is an even wilder implication. If universes can pass information forward, then, in principle, it might not just be random patterns or black hole remnants that survive. It could be possible, even if extraordinarily unlikely, for something more deliberate to cross the divide. Imagine a civilization so ancient that it lived and died before our universe began, yet with the knowledge and technology to inscribe a message in the fundamental structure of reality itself. That message could be hidden in the CMB, encoded in a pattern of temperature fluctuations so subtle that it would take billions of years for any beings to evolve capable of reading it. To entertain this possibility is to step into the realm of the almost mythic. We would be talking about a culture older than the Big Bang, one that had mastered not only the laws of its own universe but the transition between universes. Such a civilization might see the cosmic cycle as a canvas on which to leave a legacy, knowing that someday somewhere intelligent life would arise in the next universe and find the signature they had left behind. Of course, these ideas live on the speculative edge of physics, and many scientists are rightly cautious about them. The CMB is a noisy, complex data set, and the human mind is a pattern-finding machine. Sometimes we see signals where none exist. But the fact that we can even consider these questions shows how far cosmology has come. A century ago, we did not even know the universe was expanding. Today, we are entertaining the possibility that it has been expanding and contracting for eternity, with civilizations perhaps leaving whispers for their descendants in the fabric of the cosmos. And whether or not such echoes truly exist, searching for them forces us to push the limits of our understanding. It compels us to ask not just about the physics of space and time, but about the persistence of memory in a universe that seems built to forget. We have no guarantee that the answers will be comforting. They may reveal that we are part of a reality without a first moment, that the start of the universe is just a phase in an infinite pattern, and that our entire cosmic history is one link in a chain stretching beyond imagination. The thought is dizzying, but also strangely hopeful. If beginnings are illusions, then endings are too. The fall of one universe does not mean the death of all things, but the opening of another chapter. And if that is true, then perhaps nothing in existence is ever truly lost. Not energy, not information, not even the mark of lives lived billions of years before the dawn of our skies. The CMB may be the faintest whisper, but it could be the only surviving voice of an era that ended before our own began. How do we find out if that whisper is real? That is where the story turns toward the tools of cosmic decoding, the special language of the universe itself, a code we are only just beginning to learn how to read. The cosmic microwave background is not a smooth, uniform glow. Look closely enough and you'll find it rippled with faint variations, tiny fluctuations in temperature and density scattered across the sky. To the naked eye, these differences are invisible, but to the sensitive instruments of modern cosmology, they are as distinct as fingerprints. These patterns are not random noise. They are the universe's earliest signature, a direct record of physical processes that took place when everything we see today was still an unimaginably hot and dense soup of particles. In that early era, the universe was a plasma, a seething mixture of photons, electrons, and atomic nuclei, all trapped together in a blinding haze. Light could not yet travel freely because photons were constantly colliding with particles scattering in every direction. But this chaotic environment was not silent. Just as sound waves travel through the air today, pressure waves, primordial acoustics rippled through that plasma. Gravity pulled matter into clumps, compressing it, while radiation pushed back, creating oscillations. These back and forth motions, these ancient sound waves, left their imprint on the density of matter and ultimately on the CMB itself. When the universe cooled enough for atoms to form about 3,800,000 years after the Big Bang light was suddenly freed, the photons that had been bouncing endlessly were released into space, carrying with them a perfect snapshot of those oscillations. This is why the CMB is so precious to science. It is not just a picture of the young cosmos, it is a sound recording frozen in light. The peaks and troughs of those waves still exist today, stretched and shifted by cosmic expansion, but still decipherable to those who know the language. This language is written in the way the CMB's temperature varies from point to point. The size, spacing, and intensity of these fluctuations tell us about the ingredients of the universe: how much matter, how much radiation, how much dark matter and dark energy existed at the dawn of time. They also tell us about the geometry of space itself, about whether it curves inward-outward or not at all. To cosmologists, it is like reading a code that was carefully set in place 8 billion years ago, a code that has survived every star birth, every galaxy collision, every cosmic upheaval since. And here is where imagination begins to creep in. If these oscillations carry so much information naturally, then what if in theory they could also be used intentionally? The thought is almost unsettling. The CMB spans the entire observable universe, touching every point in space. Any modulation of its pattern in the early universe would in principle be visible everywhere billions of years later. That means if some intelligence, natural or otherwise, had the ability to slightly tweak the density variations in that primordial plasma, they could write a message into the very fabric of reality. A message that would endure for the lifetime of the cosmos, impossible to erase, impossible to overlook by any civilization advanced enough to measure the sky in detail. The practicalities are staggering. We are talking about manipulating matter and radiation on scales larger than entire galaxies at a time when the universe was barely a few 100,000 years old. Yet physics doesn't outright forbid it. Just as we can imagine how a drum's skin might be struck to create a precise rhythm, one can imagine a cosmic drum with density waves tuned to encode mathematical relationships, prime numbers, or even a blueprint of fundamental constants. The CMB would then carry this rhythm forward in time, stretching with the expansion of space, but never losing the underlying pattern. Even without an artificial origin, the CMB's oscillations already resemble a kind of universal script. The acoustic peaks we observe today form a harmonic series, much like the overtones in a musical instrument. They are the result of natural processes, yet they contain remarkable precision. This precision is why cosmologists can use them to measure the age of the universe to within a fraction of a percent, or to determine the exact ratio of ordinary matter to dark matter. In this way, the CMB is both a cosmic relic and a scientific Rosetta Stone. But here is the subtle, tantalizing part. A pattern in the CMB is both global and permanent, yet it is also incredibly hard to produce without access to the entire early universe. If a message were ever found there, it would instantly imply the existence of an agency with power and knowledge beyond anything we can currently imagine. It would mean that before our galaxies formed, before the first stars lit up the night, something was already thinking, planning, and acting on scales that make even our largest ambitions feel microscopic. Searching for such a signal is not as far-fetched as it sounds. Some researchers have suggested scanning the CMB for non-random sequences, statistical anomalies, or structures that defy the predictions of known physics. So far, nothing conclusive has been found. The patterns we see seem to fit remarkably well with the standard cosmological model. But the data is never perfect, and every new telescope brings sharper vision. As measurements improve, so too does our ability to notice the unlikely, the impossible, the intentional. And even if no hidden message exists, the fact remains that the CMB's oscillations are one of the most profound, natural communications we have ever encountered. They are the universe speaking to us, telling the story of its birth in a language of temperature and polarization. A story written before Earth existed, before even the Milky Way took shape. We did not invent this language yet, we have taught ourselves to read it. Each fluctuation, each ripple, each fraction of a degree is a syllable in the tale of everything. Perhaps one day, deep in that tale, we will stumble across something that does not belong, a line too deliberate, a chord too perfect. If that day comes, it will not only rewrite our understanding of the universe, but of our place in it. Until then, we listen, we measure, and we translate the silent harmonies of the cosmos, knowing that every note we uncover is a direct connection to the moment when the universe first found its voice. And then, just as we begin to feel comfortable with the patterns we have decoded, something appears, something so unexpected that it brings every neat theory to a halt. When scientists first mapped the cosmic microwave background in exquisite detail, they expected the results to confirm one of the cornerstone assumptions of cosmology, that on the largest scales the universe is isotropic, looking the same in every direction. And indeed, much of the map fit that expectation. The CMB was astonishingly uniform, with temperature variations of only a few millionths of a degree. But buried within that near perfection was something deeply unsettling. One hemisphere of the sky seemed to have a slightly higher average temperature than the other. Not just in a localized patch, not just a statistical quirk, but across half the visible universe. This asymmetry, often called the CMB hemispherical power anomaly, is not the kind of difference you can explain away with faulty instruments or random noise, not easily anyway. Careful cross-checks with multiple satellites, including NASA's WMAP and the European Space Agency's Planck Observatory, confirmed it. One half of the sky consistently appears to contain stronger fluctuations than the other. In simple terms, the universe at its most ancient visible stage seems to favor one direction over another. That alone is strange enough to keep cosmologists awake at night. The reason this is such a big deal comes down to the cosmological principle, the idea that the universe is on average the same everywhere. This principle is the bedrock of modern cosmology, allowing us to use the same physical laws and models to describe the universe as a whole. If it fails even slightly, then our grandest equations may be incomplete or subtly flawed. The early universe, according to our best understanding, should have expanded from an almost perfectly uniform state, with quantum fluctuations providing random directionless seeds for structure. There should be no cosmic arrow pointing one way more than another. Yet the CMB suggests otherwise. There are several schools of thought about what could cause such an imbalance. The most conservative explanations suggest it might be the result of statistical flukes, the kind of random deviation that's bound to appear if you only get one universe to observe. After all, probability allows for rare events. We just have no way to check against other universes to see if ours is truly special. Others propose that unknown foreground effects, perhaps subtle contamination from our own galaxy, could be skewing the data in ways we have not yet fully accounted for. But then, there are the bolder ideas. One possibility is that the asymmetry is a remnant of conditions that existed before inflation, the period of ultra-fast expansion thought to have occurred fractions of a second after the Big Bang. If the fabric of space itself had some large-scale irregularity, inflation would have stretched it to cosmic proportions, leaving behind a pattern that we can still detect today. In that case, the universe might have been born with a kind of built-in orientation, a preferred direction imprinted at the very dawn of time. An even more exotic notion is that the asymmetry could be the shadow of something enormous and hidden a structure so vast it extends beyond the observable universe, tugging subtly on matter and energy within our view. Some have speculated about giant cosmic voids, superclusters of unimaginable scale, or even contact with other bubble universes in a multiverse scenario. If our universe has brushed up against another, the encounter might have left a scar in the CMB, a directional fingerprint frozen in place for nearly 14 billion years. The difficulty is that these ideas, while fascinating, are extremely hard to test. The CMB gives us a single snapshot, a frozen image of the universe, as it was long ago. We cannot rewind and watch how the asymmetry developed, nor can we step outside our cosmic bubble to see if there's something lurking beyond its edge. Instead, scientists have to work like detectives, piecing together a case from one blurry photograph and a lot of circumstantial evidence. The stakes are high. If the asymmetry is real and caused by a genuine physical process, it would shake our understanding of cosmology to its core. The laws of physics might be subtly different in one direction than another. The universe might not be a perfectly democratic expanse of space, but rather a place with hidden biases written into its structure. Even the notion of time's arrow, the idea that time flows uniformly everywhere, could be more complicated than we thought. Some researchers have tried to connect the CMB asymmetry to other cosmic mysteries. For instance, large-scale galaxy surveys have hinted at patterns in the distribution of matter that might align with the CMB's hotter hemisphere. There are also peculiar bulk motions of galaxy clusters, sometimes referred to as the dark flow, which seem to suggest a directional pull across vast regions of space. While these observations remain controversial, the the possibility that they are all linked to a single gigantic cause is difficult to ignore. For now, the asymmetry remains one of those tantalizing anomalies, significant enough to demand attention, yet elusive enough to resist definitive explanation. It sits there on our cosmic map, a subtle tilt in the balance of the universe, whispering that perhaps we have not yet grasped the full story of our cosmic origins. Every attempt to explain it leads us down strange corridors of possibility, from the most conservative tweaks to our models, to visions of structures spanning beyond the horizon of existence. And as we stare at that imbalance, as we compare every simulation to the stubborn reality etched in the CMB, one thought keeps returning. If this is the mark of a structure, it would have to be larger than anything we have ever detected. Larger than superclusters, larger than the cosmic web itself, perhaps so large that calling it a thing at all barely makes sense. A structure not merely in space, but perhaps in the shape of space. Which leads us to the next question and the next mystery. Because if such a colossal presence exists, then we may already have seen it. In fact, it might be the single largest entity ever discovered. When astronomers first mapped the large-scale distribution of matter in the universe, they expected to see galaxies scattered more or less randomly across space like stars across the night sky. Instead, what emerged was something astonishingly organized, something that seemed almost alive. On scales of hundreds of millions of light-years, galaxies do not float in isolation, but are arranged along vast thread-like filaments. These filaments weave through space like a cosmic web, converging at dense knots where clusters of galaxies form and surrounding immense voids where almost nothing exists. It is a structure so intricate and so vast that our entire Milky Way is just a speck within a single strand. The cosmic microwave background, with its delicate fluctuations, hinted at this arrangement long before telescopes could map it directly. The patterns in the CMB are like a blueprint showing where matter would gather under gravity's influence over billions of years. When scientists overlay these predictions with observations from massive galaxy surveys, the match is uncanny. The web we see today is the grown-up version of the faint, seed-like patterns frozen into the CMB nearly 14 billion years ago. But here is where things get strange. Some of these filaments stretch not just across millions but billions of light years. One in particular, known as the Sloan Great Wall, spans about 1.4 billion light years, a size that already pushes against the limits of what cosmology says should be possible. Even more baffling are structures like the Hercules Corona Borealis Great Wall, an arrangement of galaxies and clusters so enormous it measures over 10 billion light-years across, which is roughly a tenth of the size of the observable universe. By some calculations, structures this large should not have had time to form given the age of the universe. These titanic filaments do not exist in isolation. They interconnect, looping around the cosmic voids like the strands of a colossal three-dimensional net. The density along these filaments is higher than the cosmic average, so galaxies form there fed by rivers of gas flowing along gravitational channels. In many ways, the pattern resembles a neural network with galaxies as the nodes and filaments as the synapses connecting them. The analogy is so compelling that some scientists and philosophers have wondered if the universe itself might be thought of as a kind of mind, with its vast structures playing the role of physical thought lines. If these filaments are truly as immense as the largest ones we have found, then it raises a provocative possibility they might extend beyond the boundaries of the observable universe. Our cosmic horizon, the maximum distance light has had time to travel since the Big Bang, is not a physical wall, just a limit to what we can see. There is no reason to think that matter and structure simply stop there. The filaments we observe could continue endlessly into regions forever beyond our view, linking our corner of the cosmos to places we will never be able to reach. This concept has profound implications. If the universe is far larger than the part we can observe, and almost every theory suggests it is, then these filaments could be the tendrils that connect us to realms unimaginably distant. In that case, what we call the cosmic web might only be a tiny piece of a far vaster network stretching into infinity. Somewhere along these unseen paths, conditions could be very different from our own different galaxies, different types of stars, perhaps even different physical constants. And if the filaments serve as channels for matter and energy, then in theory they could also carry information. This is where speculation slips into the realm of science fiction. But the thought is hard to resist. If a sufficiently advanced intelligence existed somewhere along these threads, it might find ways to use them as cosmic highways, not for ships, but for signals, subtle gravitational ripples or patterns in the cosmic background that could be recognized across billions of light years. From our perspective, those signals would be indistinguishable from the natural variations in the CMB unless we knew exactly what to look for. A perfectly timed fluctuation, a statistically impossible alignment of galaxy clusters, or even an engineered void, could serve as a beacon. We would not see a bright flash in the sky, but rather a quiet fingerprint in the grand architecture of the cosmos. The scale of these structures also forces us to rethink cosmic history. How could matter, starting from an almost uniform distribution, have organized itself into such gigantic patterns in such a short time? Standard cosmology explains the web's existence through dark matter's gravitational pull, guiding ordinary matter into place over billions of years. But the largest of these structures strain the timelines. If they truly formed naturally, then our understanding of cosmic evolution might be missing a key ingredient. Perhaps a faster growth mechanism or initial conditions set by physics we do not yet understand. It's possible that inflation, that brief and violent expansion right after the Big Bang, imprinted the seeds of these colossal formations. If inflation's quantum fluctuations were slightly skewed, they could have planted patterns that grew into today's superstructures. In that case, the filaments are not just scaffolding for galaxies, but relics of the very first instance of the universe. Every strand we see today could be a frozen echo of a vibration that shook space-time itself before matter even existed. For now, mapping the cosmic web is like trying to chart a continent by exploring a few scattered towns and rivers. Our telescopes can only see so far, and even within that range we have not catalogued every galaxy. But with new instruments and surveys such as the Vera C. Rubin Observatory and the Euclid mission, the map is filling in, revealing the delicate, sprawling lattice that holds the universe together. Each new discovery seems to extend the boundaries of the web, hinting that what we've seen so far might be just the innermost spiral of a structure that never truly ends. And that leads to an unsettling thought. If these filaments reach beyond our cosmic horizon, then somewhere out there, unimaginably far away, the web continues. And along it could lie galaxies. We will never see stars that will never shine for us, and perhaps civilizations that have risen and fallen without ever knowing we exist. Yet in the deepest sense we are all connected, bound together by threads of gravity, spun in the earliest moments of time. Somewhere beyond the reach of our telescopes, beyond the limits of light and time, there may be minds, not just stars, waiting along the filaments. Minds that, if they exist, might already know about us. And if that is true, then the universe is not just vast and beautiful, but perhaps also aware. For most scientists, the cosmic microwave background is the quiet hum of the universe. The faint afterglow of the Big Bang stretched and cooled over billions of years, until it now whispers to us at just a few degrees above absolute zero. It is supposed to be pure, untainted by anything that happened after the first few 100,000 years of cosmic history. But not everyone is convinced. A small yet determined group of researchers believes that buried within this cosmic static could be something else, something deliberately placed there. The idea sounds almost absurd at first, that an ancient civilization far older and more advanced than we are might have inscribed a message into the very oldest light in existence. Yet when you think about it, the CMB is the perfect place to hide a universal postcard. Unlike a radio signal that fades with distance or a laser beam that can only be aimed in one direction, the CMB is everywhere. Every observer in every galaxy on every planet sees it. It is the ultimate broadcast medium, one that requires no repeat transmission because it has been traveling unaltered for nearly 14 billion years. Theoretically, a civilization with technology far beyond our own could have altered the distribution of photons in the early universe, imprinting patterns so subtle that they would look like natural fluctuations to any species without sophisticated instruments. To us, it would appear as a slightly unusual arrangement of hot and cold spots, perhaps an improbable alignment of multipoles, or an unnatural correlation between distant regions of the sky. To them, it would be a carefully crafted code, a pattern that could only have arisen through intelligent design. Imagine for a moment what that would mean. It would be a message not aimed at Earth, not even at our galaxy, but at every civilization that ever will or ever has arisen within the observable universe. It would be timeless crossing, not just space, but cosmic epochs designed to be discoverable no matter when or where an intelligent species emerges. It would be quite literally the most inclusive message in history or prehistory. Of course, such a signal would be extraordinarily difficult to detect. The CMB is noisy in the statistical sense. Its variations are dominated by the physics of the early plasma, the influence of dark matter, and the stretching of space-time itself. To find something artificial, you would have to strip away all known natural effects, then look for the leftovers, the faint residue that resists explanation. And even then, how could you be sure it was intentional? A strange pattern might simply mean we don't yet understand the full complexity of cosmic evolution. Some theorists have suggested that the message might not be linguistic at all. Instead of words, it could be mathematics, a set of fundamental constants ratios, or geometrical relationships encoded in the temperature variations. After all, mathematics is the one language likely to be universal, understood by any civilization capable of detecting the CMB in the first place. If you wanted to announce your presence to an unknown audience across billions of years, you might choose to say something like, "We were here, and we understood the universe using the very fabric of the universe as your ink." Others go further, proposing that the signal could be an invitation, a kind of cosmic breadcrumb leading to deeper truths. If the pattern encoded a physical law unknown to us, following it could unlock technologies or insights we cannot currently imagine. It might contain coordinates in some higher dimensional space, a blueprint for energy manipulation, or even instructions for how to perceive aspects of reality we are currently blind to. The speculation is wild, but it has a strange logic. If you were a godlike engineer of space-time, why wouldn't you leave your calling card in the one place no one could erase? The implications are staggering. If such a message exists, then it changes the way we think about our place in the cosmos. We would no longer be the accidental byproducts of natural processes, but recipients of a deliberate act of communication from entities who lived, or perhaps still live, on a scale beyond our comprehension. And because the CMB is the same for everyone, the message would not be private. Somewhere on planets orbiting stars we will never see, other civilizations might already have found it, puzzled over it, or even understood it completely. But there's an unsettling side to this too. If the message is meant for anyone, then it is not just a greeting. It could be a warning, a test, or something with consequences we cannot foresee. A civilization powerful enough to alter the CMB could, in principle, have the ability to shape galaxies or manipulate fundamental forces. If such beings are friendly, that is comforting. If not, the idea becomes chilling. In that case, the CMB would not just be a neutral background, but a monument to power, and possibly to dominance. Skeptics point out that there is no compelling evidence for any artificial structure in the CMB. The anomalies we have found so far, the cold spot, the large-scale asymmetry, the low quadrupole moment, could all have natural explanations. Yet the allure of the idea persists because it is so elegantly plausible. If someone wanted to reach everyone everywhere for all time, this would be the way to do it. And unlike Radio SETI, which can fail if you simply don't point your antenna in the right place, the CMB is already in our sky, waiting for us to listen more closely. Perhaps one day, as our instruments and analysis techniques improve, we will strip away more of the noise and find a residue that refuses to go away, a stubborn signature that fits no natural model. If that day comes, the moment of realization will be unlike anything in human history. We will know that across the unfathomable distances and eons, we are not alone, and that someone long ago cared enough to leave behind a message they knew we would one day see. And even if there is no message, the search itself changes us. It forces us to look more carefully, to refine our understanding of the cosmos, to consider the possibility that intelligence might not be rare, but simply far older and quieter than we have imagined. In a sense, the very act of looking for meaning in the CMB makes us participants in a conversation we cannot yet hear, one that might have begun before the first stars lit the sky. But whether the signal exists or not, the CMB still has one more role to play. For beyond its possible secrets, there is something in it that unnerves even the most skeptical scientists. Something that has nothing to do with aliens at all, yet makes the universe feel far more precarious than we usually admit. The cosmic microwave background is often described as the oldest light in the universe, the faint afterglow of a time when the cosmos was still young and hot, when matter and radiation were so tightly coupled that light itself could not travel freely. Only after the universe expanded and cooled enough did photons slip loose, beginning their 4 billion year journey to us. Today we see them as a cold, nearly uniform bath of microwave radiation, a kind of fossil light that carries the memory of creation. But there is something haunting about this light, for while it speaks of a fiery beginning, it also foreshadows a cold, inevitable end. The CMB is not just a relic of the past, it is a preview of the future. As the universe continues to expand, these same photons will keep stretching their wavelengths, growing longer, their energies fading. 1 trillion years from now, they will no longer be microwaves at all, but long, ghostly radio waves, so faint they will be almost impossible to detect. Far beyond that, they will be stretched until their wavelengths are larger than the observable universe itself, their energy so diluted that they will no longer meaningfully exist. The afterglow of the Big Bang will vanish, and with it the last direct trace of our cosmic origin. This fading is not sudden. It is the slowest sunset imaginable, a dimming stretched across incomprehensible spans of time. Every galaxy will drift farther from its neighbors, their light redshifting beyond visibility, until each one becomes an island of stars in a vast black ocean. Even the stars will not last forever. They will burn out one by one first. The bright blue giants, then the sun-like stars, and finally the faint red dwarfs that can live for trillions of years. In the end, only dead remnants will remain white dwarfs, cooling into black dwarfs, neutron stars growing cold and dark, and the invisible gulfs between them. The CMB is our first whisper from the universe's beginning, but it will also be among the last voices to fade when everything else has gone silent. Long after the final star has burned out, these photons will still be traveling, stretched and chilled, almost to nothing, carrying a memory of a time when the universe was bright and full of possibilities. But eventually even that memory will be erased. This is what physicists call the heat death of the universe. Not an explosion or a sudden collapse, but a slow slide into uniformity, where every difference in temperature and energy is smoothed away, and no process can happen because there is no energy gradient left to drive it. It is the ultimate stillness, the final equilibrium where time itself loses meaning because nothing changes. We sometimes imagine the end of the universe as something dramatic, but the truth is more like a cosmic sigh that never ends. The thought is unsettling because it strips away the illusion of permanence. We like to think of time as an endless backdrop against which life and civilizations rise and fall, but the CMB reminds us that even the backdrop has an expiration date. Every galaxy, every planet, every memory, every trace of life, all of it will eventually be swallowed by the same fate. The universe will not just outlast us, it will outlast itself. And yet there is something strangely beautiful in this inevitability. The CMB tells a complete story, from the spark of creation to the last embers fading into darkness. It is both the opening and closing chapter written in light. We live in a brief golden middle, a time when stars still shine, galaxies still dance, and the CMB is still bright enough to see. Ours is an age when the universe is old enough to be interesting, but young enough to still be alive. Billions of years from now, no one will be able to measure the CMB at all. If intelligent life exists in that far future, they will not be able to look back to the Big Bang in the way we can. To them, the universe will appear eternal, and static its origins hidden forever. Perhaps this is what makes the CMB so poignant. It is a privilege of our cosmic moment. We are among the rare observers who can still see the universe's birth certificate before it fades away. That awareness brings a kind of urgency, a reminder that even the grandest things are temporary. Time and space themselves are on a clock, and the CMB is the ticking. This perspective can feel crushing, but it can also be freeing. If everything must end, then the value of things is not in their permanence, but in their existence at all. Our lives, our civilizations, our art and science, all are brief sparks in a long night, but sparks nonetheless. They matter because they happen even if they cannot last. The CMB's eventual disappearance is not a tragedy in itself. It is simply the nature of the universe to evolve, to change, and eventually to let go. In a way, the fading of the CMB mirrors the fading of individual lives. Just as the universe will one day lose its light, so will each of us. Yet knowing this does not stop us from living, from creating, from loving. The point is not to last forever, but to be part of the story while it is still being written. The CMB is the opening chapter of the greatest story ever told, and we are lucky enough to read it before the ink disappears. But here is the quiet twist. If there truly is an end, that also means there was a beginning. And if beginnings are possible once, they might be possible again. The death of everything may not be the last word, only the end of one sentence in a much longer cosmic narrative. Some theories even suggest that the universe could be reborn in a new Big Bang after its long heat-death slumber, starting the cycle anew. If that is true, then the CMB is not just a relic of the past, but a promise that beginnings can happen and that somewhere beyond the horizon of our own end, the light may rise again. The idea that the universe might not be a one-time event but part of an eternal rhythm of birth, death, and rebirth is as old as human imagination. Ancient myths from many cultures told stories of worlds destroyed and made anew, of cosmic fires, extinguished and reignited, of time itself looping like the seasons. Today, some modern cosmologists find themselves echoing those ancient tales, but in the language of physics. Instead of gods or dragons, they speak of entropy and singularities of energy fields and space-time curvature. Yet the underlying story is strangely familiar. The universe dies, and then it lives again. In this picture, the heat death of the cosmos is not the final curtain, but merely an intermission. After an unimaginably long period of stillness, when every star has faded and the CMB has been stretched into invisibility, something stirs. Perhaps it begins as a fluctuation in the quantum vacuum, or as a slow collapse of space-time itself. Perhaps the expansion reverses the great cosmic stretching, slowing, halting, and then running backward, pulling all matter and energy inward, until the universe is crushed into a single, impossibly dense point. This is the Big Crunch scenario, where everything returns to the same conditions that existed before our Big Bang, only to explode outward again, beginning a new cycle of creation. Other theories imagine a gentler rebirth without the violence of a total collapse. In some models of cosmology, the very fabric of space is linked to a field that can undergo phase changes, like water freezing into ice or boiling into vapor. A phase change in the deep structure of space-time could ignite a new burst of expansion, seeding a fresh universe even as the old one drifts into silence. In this case, our CMB, the faint microwave glow we study today, would be the last surviving trace of the previous cosmic era, the ashes left over from a fire that once burned as brightly as our own. This is a humbling thought. What we see as the dawn of everything may in fact be the residue of something much older. Our universe might not be the first or the most advanced or even the most interesting. We could be living in a middle chapter of an infinite book, where the same fundamental laws play out in countless variations. The CMB becomes, in this view, more than just a scientific clue to our own beginnings. It is also a mirror showing us the faded reflection of a cosmos that once lived, thrived, and eventually died, leaving behind only this thin afterglow. It is tempting to imagine what those earlier universes might have been like. Were they filled with galaxies and stars like ours? Did life arise? And if so, did it gaze upward and wonder about its own origins? Could there have been civilizations that learned to read their own version of the CMB, decoding the final whisper of their cosmic ancestors? And if so, did they try to leave a mark, some kind of message or signal embedded in the very fabric of their universe, knowing it might be the only thing to survive into the next? If cycles of universes are real, then time becomes less a straight line and more a spiral, each loop building upon the last. The end of one universe is the seed of the next, and the Big Bang is not an absolute beginning, but a rebirth. In this spiral, every CMB in every universe is both a relic and a legacy, the final word of one cosmic story and the prologue to another. Ours, then, is part of a chain of light, stretching back through an unknowable number of past universes, each linked by the faint radiation that endures beyond the death of everything else. This vision can be dizzying. It takes the comforting idea of a single origin and replaces it with an endless series of origins, each just one frame in an eternal reel. Yet it also offers a strange kind of hope. If the universe can be reborn, then nothing is truly lost forever. The stars will come again, the galaxies will swirl again, and perhaps, just perhaps, life will emerge again to wonder at its place in the grand pattern. Some physicists even speculate that we might knowingly or not be contributing to that next cycle. The laws of physics are written into the structure of space-time itself, and every interaction, every particle, every fluctuation leaves an imprint. If a new universe blooms from the remnants of ours, those imprints might be carried forward in subtle ways. It is not inconceivable that the shape of our universe, the distribution of matter and energy, and even the patterns in our CMB could influence the initial conditions of the next cosmos. In that sense, we are all participants in a much larger story, our existence woven into the deep memory of reality itself. From this perspective, our CMB is like a photograph of a fire we did not start, but now tend in our own brief way. We are looking at the embers of a blaze that once consumed an entire universe, trying to read its history from the patterns of smoke and light. And whether we realize it or not, we are also adding our own threads to the tapestry threads that might one day be glimpsed by beings in a universe yet unborn. It is a concept that collapses the distance between science and myth. The ancient storytellers who spoke of worlds dying and being reborn were in their own way describing the same thing our equations now suggest. The language has changed, the symbols have shifted, but the idea is the same. Darkness gives way to light, and light eventually returns to darkness in an eternal dance. If the cycle is real, then somewhere in the deep future, long after our stars are gone and our CMB has faded, another universe will awaken. Its own version of the CMB will bathe it in a faint glow, a glow that might contain echoes of our existence. And perhaps on some distant world in that future cosmos, curious beings will look up and wonder where it all began, not knowing that in a very real sense they are asking about us. Right now, every photon streaming from every star, every galaxy, every quasar in our universe is on a journey that will outlast the worlds that gave birth to it. The light we see when we look through a telescope is not static. It is stretching its wavelengths, pulled longer and longer by the relentless expansion of space. Eventually, even the most energetic beams of starlight will be dragged into the cold depths of the microwave spectrum, fading into the same soft background hum we now call the cosmic microwave background. Only this time, it will not be the echo of our Big Bang, but the afterglow of our universe itself, the last signature of everything that ever happened here. In the far future, when our stars have burned out and the sky has gone dark to any creature with eyes, the remnants of our light will still be traveling. They will be carried on the swelling tide of space, until at last they blend seamlessly into the background radiation of a newborn cosmos. If the cycle of universes is real, then the CMB of that next universe will contain hidden in its subtle fluctuations the fingerprints of ours, not in words or images, but in patterns of energy that tell the story of all we once were. It is an unsettling and beautiful thought that we, without knowing it, are shaping the first light of another reality. Every supernova, every swirling galaxy, every collision of black holes is like a stroke of paint on a vast cosmic canvas that will one day hang in the sky of a future world. The beings who might live there, looking out across their own deep past, could trace faint structures in their CMB and wonder about the forces that shaped them. They might ask themselves the same questions we do now. Was there a beginning? What came before? Are we alone? And what lies beyond the edge of everything we know? Our role in that story is passive, yet profound. We are not consciously sending a message into the future, yet the record of our existence is being etched into space-time itself. The galaxies that now shine are broadcasting their histories simply by existing, by radiating light that will never stop moving forward until it becomes part of something else. Long after our civilization is gone, long after the last human thought has faded, the universe will continue its slow transformation into the background glow of another age. Imagine a distant era when no trace of our world remains, except in the statistical noise of a cosmic photograph taken by alien scientists in another universe. They will not see our cities or our art, our languages or our faces, but they may see the shadow of our Milky Way written in the large-scale structure of their sky. The faint, cold patches in their CMB might correspond to vast clusters of galaxies we once saw blazing with light. The warm ripples might be the stretched and cooled embers of our most violent events, the collapse of massive stars, the dance of merging black holes, the quiet death of light itself. To them we will be as unknowable as any vanished civilization is to us. And yet we will have left something behind whether we intended to or not. That is the strange gift of the cosmos. It records everything not in books or monuments, but in the shape of its own energy. Our present becomes someone else's prehistory. Our questions become echoes in the minds of creatures who will never know our names. The symmetry of this is striking. We peer at our own CMB and search for signs of an earlier universe of patterns left by forces or beings that came before us. We sift through the static, hoping to find meaning in its faint, random-looking fluctuations. In doing so, we are unknowingly rehearsing the same act that may be performed billions of trillions of years from now by minds in another cosmos. They too will stare at their ancient sky, hunting for some glimmer of origin, some hint that they are part of a story larger than themselves. Perhaps they will sense that the noise is not just noise, that it carries the fingerprints of an entire universe now gone. They might build theories about the strange shapes and irregularities, speculating about long-dead stars and vanished galaxies. They might imagine beings like themselves living in worlds of rock and gas and water, asking the same questions. And in a way, they would be right. The record is real, even if they cannot read it in the way we might wish. This continuity, this passing of the torch from one universe to the next, makes the CMB more than just a snapshot of cosmic infancy. It becomes a bridge, a connection across the abyss of time. We are the recipients of light from a universe's first moments, and we are also its contributors, sending forward our own last light to seed the background of what comes next. Every second, we are both looking back and giving forward part of a chain that may never end. The poignancy of that idea is difficult to ignore. It means that even in a universe that will eventually fade to black, there is a kind of immortality, not for individuals, not even for civilizations, but for the patterns we leave behind in the fabric of space. Our role may be small and our awareness of it fleeting, but the imprint is there, written in the quiet language of physics. And so the next time we look at the CMB, we might think of it differently, not just as the relic of our own beginning, but as the echo of someone else's end. And when we imagine the future, when our light has cooled and merged into the hum of another universe, we might take some comfort in knowing that somewhere far beyond the horizon of our time, curious minds could be wondering about us, just as we wonder about the ones who came before. In that way, the question they will ask, what lies beyond this curtain, will not only be a reflection of ours, but its continuation. A mirror stretched across universes, returning the gaze of minds separated by eternity. yet linked by the same unending search for the truth. Perhaps the most haunting truth about the cosmic microwave background is that it might be nothing more than a limit, a wall beyond which we cannot see. We treat it like a treasure, a precious photograph from the universe's earliest moment, but it could just as easily be a ceiling painted with stars, a beautiful but impenetrable boundary. The photons we collect from it have traveled for nearly the entire age of the cosmos, yet they may be telling us only the most superficial part of the story. For all our instruments and equations, we cannot say with certainty what lies beyond that soft, static glow. Some cosmologists argue that there might be nothing at all beyond it, that the universe as we know it began at that curtain, and that there is no deeper backdrop, no hidden machinery. In this view, the CMB is not a doorway, but the outer skin of reality itself, stretched tight around the space-time bubble we inhabit. Others suspect that what we see is just the surface of something far grander, an outer layer wrapped around a vast and possibly infinite structure. This difference is more than academic. It shapes how we think about our own place in existence. If the CMB is all there is, then the universe is complete and self-contained, a single, unbroken whole. But if it is merely a shell, then the true cosmos may be vaster and stranger than anything our minds can yet hold. The metaphor of a stage curtain is more than poetic. In a theatre, the curtain hides everything that has not yet been revealed. You may hear hints, muffled voices, the clink of props, but the scene remains a mystery until the fabric is drawn back. With the CMB, we are in the same position, sitting in the darkened audience, staring at a shimmering veil that will never be pulled aside for us. We know there is something there, even if that something is only more space, more time, more emptiness. And like any great performance, the power lies partly in not knowing what comes next. Our attempts to pierce the CMB's mystery are both brilliant and humbling. We build satellites that can measure temperature differences of a few millionths of a degree, map the sky with exquisite precision, and tease out subtle ripples that hint at the seeds of galaxies. Yet no matter how sharp our images become, the CMB remains a flat and finite surface. It tells us about the universe as it was when it became transparent, but not about what came before that transparency. It is as though we are staring at the first frame of a film and trying to guess the entire plot. The truth is, we might never know. And that is not necessarily a defeat. The absence of an answer is not a void. It is a space where imagination and curiosity can flourish. Just as explorers once stood at the edge of an unknown ocean, unsure if they faced endless water or another shore, we stand at the edge of the observable universe, unsure if the CMB is a final horizon or merely the first page of a much longer story. The map ends here, but the world may not. If there is a deeper realm beyond the CMB, it might hold the relics of a universe before ours, or entirely different laws of physics, or even infinite variations of reality, where every possibility plays out somewhere. It could be chaotic and formless, or it could be an elegant, ordered structure from which our universe sprouted like a bubble from foam. But it could also be empty, truly empty, in a way that is hard for human minds to grasp. This possibility, stark as it is, has its own beauty. For even if the curtain hides nothing, the act of wondering what might be there has driven some of the most profound leaps in science and philosophy. That perhaps is the real gift of the CMB. It does not give us the final word on the universe, but it compels us to keep asking questions. It reminds us that our knowledge is always bounded by what we can observe, and that beyond those bounds lies a vast territory of possibility. Whether the truth is grand or mundane, the fact that there is still a question is itself a reason to keep looking. The mystery is not diminished by the lack of an answer, it is sustained by it. So imagine for a moment that you are looking at the oldest picture of the universe. You see faint ripples of temperature, ancient light stretched thin by eons of expansion. You know that this is as far back as you can look, that no telescope will ever see beyond it. And yet instead of frustration, you feel a kind of quiet exhilaration. Because the real treasure is not the image itself, but what it stirs in you, the knowledge that there is more to seek, more to imagine, more to understand. In that moment, the CMB stops being just data, just photons on a sensor. It becomes a mirror, reflecting not only the cosmos but your own mind, the part of you that hungers to know. You realize that your curiosity is its own form of light, capable of traveling farther than any beam in the physical universe. And while the CMB may be the boundary of what we can see, it is not the boundary of what we can dream. So let the curtain remain. Let it hang there, shimmering with the faint glow of the first light. Not because we have given up on pulling it back, but because part of the wonder is knowing that somewhere beyond it there is still a mystery worth chasing. In the end, the CMB may turn out to be the universe's greatest gift, a reminder that even in the face of limits, our imagination knows none. And perhaps that is the true ending of this story, the realization that the only light that truly pierces the darkness is not just the afterglow of creation, but the restless, unquenchable spark within us.